Right, yesterday we looked at the partial fractions, and we saw that the fractions basically either end up with a linear function on the bottom, and that's easy, that's always going to turn out to be log, or a quadratic. So let's have a look at quadratic denominators. Okay, what could we end up with? We could end up with the difference of two squares on the bottom. And yep, I could go and do that via partial fraction. My recommendation is that you actually remember these integrals. These are, if you like, the missing standard integrals that didn't even appear on the old sheet. They're not on the new ones either, but you can save yourself a heck of a lot of time. So, yep, if you forget what they are, you can do them via partial fractions and do it that way. There we go. They turn out to be very similar. 1 over 2a log, and the question is, how do we remember about the fraction? If I finish with the x, I finish with the minus x. See how, look, minus x squared, finish with minus x. Starts with x minus, start with x minus. There you go. Okay, the other ones which do appear on the standard integrals, now, of course, these aren't the standard integrals we're going to get anymore. However, in our next extension 2 task, which will be on integration and volumes, we are going to put the old standard integrals in there. Unfortunately, in the HSC, there won't be those ones, and so therefore in the trial, we'll put the new one in there as well. But it's on both of them anyway. There's our inverse tan if it's the sum of two squares. Now, the other possibility we could have, which we didn't really deal with the partial fractions, is what about if it's the square root? The square root of a quadratic. And so we know we've got our inverse sine, or if you prefer, minus the inverse cos. Then we have this one. Now, it did appear on the old standard integrals. It's not on the new ones. I don't know why. But have a look at these two. They're very similar again. X squared minus a squared, and this one's a squared plus x squared under the square root sign. But notice the square root matches. So it's both of those basically are the log of x and then plus the square root of whatever the square root is. Okay, let's do one. X squared plus 4x plus 9. Now, every one of those standard integrals is just got two terms. So basically what we've got to do is complete the square. So we end up with two terms. We get two squares. So x squared plus 4x plus 9 becomes x plus 2. Remember, it's always half the coefficient of x. But of course, if we were to expand that out, we're not going to get 9. We'd get 4. So I have to add 5. So it's in the form x squared plus a squared. X in this case is x plus 2. A in this case is the square root of 5. But that's an inverse tan. So we get 5 times 1 on a we said was the square root of 5, inverse tan of x we said was x plus 2, over a we said was the square root of 5. So there's our answer, and we just tidy up the coefficient there. We've got the square root of inverse tan, x plus 2 on the square root of 5. All right, let's try this one. Here's one where there is a square root. We've also got a 3x plus 2 on the top, you'll notice. And all of those standard integrals just had dx on top. It didn't. So basically a constant. So we've got to deal with that as well. So how do I do that? I split it up into two integrals. What do you notice about the first integral, what I've done to the numerator? Now, I haven't just randomly picked things to write down. There is a pattern there. Anyone notice it? Yeah. It's the derivative of the quadratic. Because that way, I'm not going to, well, I probably did do in my theory here. In reality, I wouldn't show the substitution step, because in my head now, I've created du over the square root of u. Du over the square root of u, and I know I can integrate that. That's going to be 2 root u. 2 root u. But of course, I can't change the question. So I just look at the x's to see what number to put out the front. It was 3x. I've turned it into 2x. Can't change it. So to get that 2x back to 3x, I've got to multiply by 3 on 2. So that becomes the fraction out the front. But of course, that now means my constant has changed as well. So if I was just to leave this there without the second integral, I'd go 3 on 2 times negative 4. That gives me negative 6. But the constant is positive 2, so then I have to add 8. But the second integral is now the constant over that quadratic. So in the second one, I will complete the square for the quadratic to see which one of the standard ones it is. The first one, as I say, ends up being du on root u. If you don't see it, there's the substitution. U equals what's under the square root sign. That's what's causing me the problems. So du equals 2x minus 4. Oh, whoa, isn't that amazing? That's the numerator. Not a coincidence, of course, because that's what we put there. So we get the du on root u that we were looking for. Now, the completing the square. Again, I know it's going to be x and then half the coefficient. So half the coefficient of minus 4x is minus 2. If I was to expand that out, I'd get positive 4. I want positive 1, so I've got to subtract 3. So I've got the square root of x squared minus a squared, which the biggest mistake is to say, oh, that is, what would the mistake be? Yeah, a lot of people go, oh, that's inverse sine. No. Inverse sine is a squared minus x squared. So this is the, it is on the old standard integral sheet. Let's see if I remember. That's the one that goes log of x plus the square root. Okay, but x in this case is x minus 2. A in this case is root 3. So let's tidy it all up. 3 on 2 times 2 root u. That's the integral of root u. Then I've got log, 8 out the front, of course, x, but x is now x minus 2, plus, and the square root, remember the square root was always just the same as what was in the question anyway, so the square root of x squared minus 4x plus 1. Just got to substitute in for u here if I do use the substitution method. And so there we go. We've got 3 times the square root of x squared minus 4x plus 1 plus 8 log x minus 2 plus the square root of x squared minus 4x plus 1 plus a constant. All right, this is where you're now looking at the example and saying, hang on a sec, you've gone crazy. That's not a quadratic. But it will become a quadratic. Because what I'm going to do is something we do a lot of, but not actually. What? I'm going to rationalize the numerator. We rationalize the denominator a lot. We don't often rationalize the numerator. So I'm going to multiply by the square root of x plus 3 on x plus 3. Why do I do that? Because now look at my question. It's a bit like the last one, where I've got the square root of something on the bottom, a quadratic, and on the top, I've got x plus 3. So again, I'll split this into 2 integrals. The first integral, on the top, I want to put the derivative. So I want minus 2x minus 1. Got to balance it out. Let's have a look at the x's. I've got minus 2x, but originally it was just positive x. So I need to multiply by minus a half to balance that out. Now let's look at that constant. What have I done to that? Minus a half times minus 1 is positive 1. Well, sorry, positive 1/2. I want 3. So I've got to add 2.5, which is 5 on 2. Not quite sure why I put the 5 in the integral and the half on the outside the integral. I suppose it doesn't really matter. I could have put the 5 on 2 out the front. All right, but again, look what we've ended up with. Du on root u. So I know that's going to be 2 root u. This is what I was saying before. Some of these integrals, if you just remember, can save you time. Because that's going to be 2 root u, cancels with the half, or the minus half. I'm just going to have minus the square root of 6 minus x squared. Second one, I've got to complete the square. Oh, a little bit nasty, but there it is. Complete the square. Few things we have to be careful with here. Notice I've taken the negative out as a common factor. Because, of course, when we square our binomial, we're always going to end up with plus x squared. So I need to have the negative out the front, so I end up with the negative x squared. So that's why I factorised the negative out there. That now means the coefficient of x is not minus 1, it's now plus 1, because I've factorised the negative out. And half of 1 is a half, so I actually end up with x plus a half all squared. And if you feel a bit unsure when you're doing that, we'll simply expand out and make sure it does work. But the number, if I've got minus a half squared, well, that's minus a quarter. I want positive 6. So to go from minus a quarter to positive 6, I've got to add 6 1/4 which as an improper fraction, 6 fours are 24, 25 on 4. And there's my 25 on 4. So, it's a squared minus x squared. A in this case is 5 on 2. X in this case is x plus a half. So it is an inverse sign in this time, but you might be thinking, oh no, look, you've made that silly mistake of putting 1 on a out the front. No, I haven't, because look at the integral. It had 5 on 2 out the front. So that's where my 5 on 2 came from. It does not have the 1 on a out the front. But we get inverse sine of x plus a half over 5 on 2, but I've inverted and multiplied there, so I get 2 on 5. And over here, there's my 2 root u. And it tidies up to be, well, quite reasonable. Minus the square root of 6 minus x squared plus 5 on 2 inverse sine of 2x plus 1 on 5 plus, of course, a constant. All right, so as I say, the missing standard integrals that are good to remember. There it is. Dx on the square root of a squared minus x squared. Now, new way of remembering this is not that when they factor it starts with, Look, it's a minus x, so it finishes with the minus x, so I finish with the minus x on the bottom. We all know what's going to happen now. X squared minus a squared. Oh, look, integral begins with x. So primitive begins with x. All right. Oh, they were the old missing ones. And, of course, now the other missing one is that log of x plus the